They go as a KDC as patient 0 for a real ticket to the workstation. They get it. They're able to unwrap it, unwrap the session key, and have the real ticket to the server issued by the real KDC. They rewrap it with the key they've controlled and given to the victim, send it along. This is a referral TGS reply because the name is different than the name that the victim thought. This will be accepted and they can use it to log in. So now we have a situation where the victim has logged in with their smart card, but they came in as somebody else. So is this really an elevation of privilege? You know, we assumed at the beginning we had control of patient 0, and now we have a login session as patient 0. So we haven't elevated privilege yet, but we're in a very good position to, because a user started at a trusted, healthy workstation, has no malware on it whatsoever. They put their smart card in, they typed in their PIN, and they got logged on as someone else. They have no reason to expect that that's going to happen. That's completely unusual behavior. And furthermore, that login interactive session now we control. We have control of that patient 0 account. We have control of the KDC. We can change their login environment. We can run commands on that desktop. We can push group policy. So we'll push a Trojan that pops up the screen as soon as they log in that says, installing updates, please do not turn off your computer. And we hang around for 10 minutes, and then we pop the screen that says, insert your smart card to unlock your workstation and type your PIN. User types in their PIN, it unlocks, says, please wait, we're rebooting. They reboot, they log in again, everything's fine. But what really happened was they forgot to hit Control-Alt-Delete. Pretty common. They're used to putting in their smart card and typing their PIN. They think it's a trusted system. But really that Trojan program just captured their PIN. In user mode, it's able to unlock the smart card module, make a TGS request to the real server, and now it has a credential it can renew for up to 7 days and access any service in the enterprise as that user. Smart card TGTs also contain an additional field, supplemental credential buffer, that has your NTOWF in it so that you can do NTLM authentication. And for smart card only users, that doesn't change pretty much forever. So now I can also have a very long-term credential that lets me authenticate to any service in the network that accepts NTLM. So we basically started with one computer and one user, and we're able to, by network attacks, silently elevate and take over any other user's credentials that uses smart cards to log in. This is a complex and difficult elevation path, but it also leaves almost no forensic traces. The protocols can't be firewalled. They're all the same normal protocols you need to log onto your domain, and all of the things that are different about the attack versus the real protocol are hidden inside the encrypted portions of the protocol that a network sniffer can't see. And as I said before, IPsec and DNSSEC won't save you. So what would we do about this? Well, we have that strict KDC validation policy I mentioned earlier. You can turn that on for Vista SP1 and above. It is not available for Windows XP, but frankly, if you're worried about this level of attack and you're running a 7-year-old operating system, you probably have bigger problems and you need to get working on that first. Before you can turn on this policy, you need to enroll all your domain controllers for an updated certificate. The template is available in Windows Server 2008 and above. It's the Kerberos authentication template. The reason these policies aren't default is because older KDCs would not have this, and if you just turn on this policy, nothing would work. So enroll your KDCs first and then turn on the policy. For domain join, it's very hard to push policy and secure this before you join to the domain, since the domain is usually your mechanism for policy. So either set this policy on your system images, domain join offline, use a password for joining to the domain, and audit who is able to and who has actually joined machines to the domain. On the typical open source clients, they do supply the CKU with their standard server certificate tools. So if you're in a purely Unix or purely Linux environment, this probably doesn't apply. But if you are in an environment where you're interoperating with Windows and you have this require EKU flag turned off, you can turn it back on after you've updated your certificates on your domain controllers, and then you'll be safe. And really, there's a lot going on here. I've just kind of glossed over the top of it. So I would encourage you to go visit ISEC Partners' website. There's a 20-page paper we're going to release later today describing the attack in a lot more detail and a bunch more hardening recommendations. And Microsoft yesterday also published a 20-page paper giving step-by-step instructions for network administrators to enable all the flags and secure against this attack with screenshots and the whole deal. I would put the link up, but it's about 150 characters long and has a GUID in the middle, so it won't do you any good anyway. So just go to isecpartners.com and we'll have a pointer to that for you later today. So we've bemoaned and attacked initial authentication, but that's only sort of just incidental to the process of Kerberos. What we're really trying to do is get service from an application. And there are a whole other set of pitfalls that come with that, and I'm going to hand that over now to Rachel Engel to discuss those.
Thank you, Brad. So at this point, we have typed in our password, and we have gone to the KDC, and we've got a ticket to talk to the service that we want to talk to. Ultimately, though, your reason for using Kerberos is to check email or connect to LDAP, and that piece of the protocol is happens with the AP rec and the AP rep. This is a request and response. So what happens there is you send a request, and when you send that request, at this point, the client has a copy of a session key. They send the request, and the request contains a copy of the session key that can only be read by the service. After this request and response happens, both the client and the service have a copy of the session key. A lot of the time, Kerberos is called a single sign-on protocol, but what it's really good at is establishing a session key between two authenticated principals on your network. So we've established this session key between the client and the service. But have we authenticated yet? Well, not really. The service has this key, but does it know who the client is? No. It has to have some information from the client that it can use to determine whether or not the client is the person it intended to talk to. And that comes in a piece of data called the authenticator. So the server decrypts its session key. It takes that and it uses that to decrypt the authenticator, and then it looks at the information in the authenticator. But think about this. All the client has done to authenticate is send a request. So what's to stop an attacker sitting in the network from taking a copy of the request? Nothing initially from what we've talked about so far. You can take that, Mallory, if no protections are in place, can take that request, send it on to the service, and authenticate as the user. If the developer isn't careful, this works. This requires developer care to prevent, and so we'll go into that. How do we prevent this? Well, the authenticator, it contains a couple of pieces of information, and if you look, some of those pieces of information are designed to at least do some prevention of replay. One of them is a timestamp. This is used to determine the freshness of the ticket, so if Mallory gets a copy of that request and then goes away, has lunch, comes back later, tries to use the request, at that point it's not going to work because it's not going to fit within the freshness window. But the timestamp is just big enough to detect clock skew, but if Mallory is actively editing the traffic in the network, Mallory is going to be able to beat the freshness window, so this is not going to stop Mallory. There's a replay cache. The service takes a copy of the request, stores it, and then looks and sees if subsequent requests are the same request, and if it's the same request that's already received, then it's a replay. However, if Mallory is sitting there on the network actively editing the traffic as it goes across, Mallory can win and have the first request, so the local cache isn't going to stop it. There's also a checksum. This is more interesting. So the checksum can take a checksum over application data. That also goes in the authenticator. But if you think about it, a single checksum at the time of authentication isn't good enough to provide integrity for a full bidirectional protocol. So what do people do with it in practice? People do lots of things with it in practice. Sometimes they set it to nothing, which does really no good. RCP sets it to a checksum of the contents of the command line arguments. SSH sets it to a magic number. It is not a random number. It is not particularly entropic. It is a magic number, but it is effective. If I take a request that was sent to authenticate another service like Telnet, and I try to use it in the context of SSH, SSH is going to check the checksum and see that Telnet did not set the checksum to anything, and it's looking for its magic number, and it will reject it. So effectively, it's an informal service binding, which means that you can only do replays again, that have been of requests that have been intended to be sent to that service. So if none of these pieces of data prevents a replay, what do we do? You'll perish in flames. Well, you will not perish in flames. It is not quite that bad. Earlier, I said that what Kerberos is really good at is establishing a session key between two authenticated principals on a network, and it is very good at that. When the request and response have been sent, both the client and the service have a session key. This session key can be used to do integrity protection of the protocol. So I'm developing a protocol, and what I need to do when I authenticate with Kerberos is take that session key and use it to provide integrity. If Mallory at this point goes and takes the request and tries to send it to the service, perhaps it will not be detected as a replay, but when Mallory tries to start sending traffic, it will be noticed as being inauthentic because it does not have the integrity protection that's appropriate. So this actually works, and this is effective. This is why the attack is possible, because preventing it requires developer care. So what we can do is developers should be careful to integrate the session key into the integrity protection for the protocol. Administrators should look at their Kerberos deployment and check the services to make sure that the integrity protection is integrated with authentication. Also, since Mallory was getting the copy of the request by intercepting traffic on the network, also having some encryption and integrity between the two endpoints via Stunnel or IPsec would prevent Mallory from getting the request in the first place. Although if Mallory breaks the security guarantees of either of those protocols, then the same advice still applies. The session key established authentication needs to be integrated into the rest of the protocol. And for what to do on Windows, I'm going to hand it over to Scott.
Hi, as Rachel noted, in the Unix world, you typically will be using Kerberos quite directly. And there are a couple of other APIs you can use that will use Kerberos under the covers. But in the Windows world, you're almost certainly abstracted from the details of Kerberos via an interface called the Security Service Provider interface. Now, you can use SSPI directly to roll your own use of the negotiated security service providers, one of which is Kerberos, others are NTLM, and so on. You can use that directly if you want to roll your own cryptographic binding, and that's something that people might do with just a raw TCP socket. But the other 99% of Windows developers are almost certainly going to be relying on the integrated Windows authentication that you get for free when you use major protocols that are exposed in Win32. So in order to make that cryptographic binding that Rachel talked about, making it so that the application protocol has at least integrity protection, maybe integrity and privacy, then you have to use the application programming interfaces for those protocols correctly. So let's go through those protocols one by one. LDAP. LDAP is used in Windows to communicate with the KDC primarily, but it can be used for many other things. There are two major APIs that Win32 exposes. One is called, I'll just call it the LDAP API. I'm not sure if it has a better or more specific name, but what's great about that API is you can specify the specific SSP you want to use. You can say that you want to use Kerberos with it, and then there are also flags for requiring integrity or integrity and privacy. There is another API that's available called ADSI, which is widely used, and it's a little bit more Active Directory friendly. However, it doesn't allow you to specify the SSP. You can specify whether you require signing or signing and sealing, meaning integrity or integrity and privacy. You can specify that. However, you can't specify that you want Kerberos and all the goodness that Kerberos provides. If you do want to use ADSI and you do want to make sure you use Kerberos, best way to do that is to have the administrator turn off NTLM on your clients and servers, which is an option that's available with Win 7 and Windows Server 2008 R2. Now, RPC is purely over in the developers world. RPC